Hey guys, you have learned about both arithmetic and geometric sequences at this point, and we're going to take it to another step. This title of this unit is called Sequences and Series, and so we're going to look at series. And to do that, we also need to understand summation notation. So series and summation notation. And so just to clarify the difference between series and sequence, which just in the English language, a lot of people use interchangeably, but really and truly a sequence is something like 2, 5, 8, 11, I'm just going up by 3, and it's just a list. So this is our sequence. But if we were to take them and add 2 plus 5 plus 8 plus 11 and so on, then it is called a series at that point. Okay, so I'm going to get you into the notation of things a little bit. We use the Greek letter sigma, and this sigma will represent a sum, and so that will mean we're actually adding them up. And next to that sigma, we'll put the explicit rule. And the explicit rule, I'll explain why I'm using a sub k instead of a sub n, is what creates those different terms in your series. And down at the bottom underneath, kind of subscript style, we'll put something like k equals 1, and at the top I'll put n. This k equals 1 is called your lower bound. And the lower bound is going to be the first number that you plug into your explicit rule to start building out the series. And so this is the first value plugged in. And then up top we have n. This is our upper bound. And this is the last value that we plug in. Okay, and then just a couple little notation things. The lower bound's variable and the variable that's in your explicit rule, those have to match. So I'm writing variables must match. But they also have to be different than the upper bound's variable. So they have to match and be different than the upper bound. Okay, and so that'll make more sense when we actually see some values in place of all of this. Now, when you guys write out a sigma, you don't have to always make it so perfect. Sometimes I'll just kind of squiggle it in real quick. And so I just want to give you a little scenario. So for our first example, I'm going to take the sigma k equals 2 to 7 of k squared. And so I want to make sure you know how to read this and what it means. I would read this out loud as the sum of, and I would say the sum of all of the terms in k squared as k goes from 2 to 7. And so we are going to expand that out first by plugging in 2, plugging in 3, plugging in 4, 5, 6, and I stop when I plug in 7. So I plugged in my lower bound first, and I stopped when I plugged in my upper bound. Do not put commas. You want to have plus signs in between because this indicates that we're actually going to add these up, which is what the sigma summation symbol means. And then from there, you can actually go ahead and square all of your numbers and sit and add them all up. And we get 139 for that. All right, so what I want to point out is when you write it out in this way with the plus signs separating the terms, but we can actually still see all of the terms, this is called expanded. So if I ask you to expand the sum, I want to see something like this. And if you actually calculate, well, what do you get when you add all those numbers up? That's called evaluating the sum. So expand the sum or evaluate the sum. Okay, so if you do both, it's not necessarily wrong, but sometimes you can't do both. So for number 2, I'm going to ask you to just expand the summation as k goes from 1 to n of, we'll do a weird one, 1 over 1 minus k. So far k squared, that's not arithmetic and that's not geometric. 1 over 1 minus k is also not arithmetic and not geometric. This is a rational function and this is a quadratic function, but they don't fall into that umbrella of arithmetic or geometric. Okay, so if I expand this, I'm just going to start by plugging in my lower bound. plus sign to separate terms. Then I'm going to plug in the next number after 1, so 1 minus 2 on the bottom, 1 over 1 minus 3, and so on. And we would keep doing this until, doesn't really say when. So we keep doing this until we get to the nth term. To indicate that, we put plus dot 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 plus, and then you plug in your upper bound of n. Now this one will look a lot better if you clean it up a little bit. Oh wow, that's a big typo there. I had 2 on my paper and was like, oh, let's just start at 1. I need to change this one so it's k equals 2 at the bottom, because that brings up a whole nother conversation. 1 minus 1 on the bottom here is actually 0. We cannot divide by 0. 1 divided by 0 is undefined. It causes asymptotes on graphs, a whole lot of stuff happening there. So I'm actually going to change that lower bound to 2 and take off that first term. Our expansion would still look similar, but now when I simplify it, it'll make more sense. This is a 1 over a negative 1, which is negative 1. And the next one is 1 over 1 minus 2, which is going to be a negative 1/2. And I just simplified that plus a negative and called it minus, which is all fine. So this would be my expanded form. Okay, there's another case I want you guys to expand because it has just kind of a different little notation at the end. I'm going to go k equals 1. I'll do k equals 0 actually to infinity of 3 times 1/2 to the kth power. So this time we do have a geometric sequence. You can see the common ratio in the base there. I'm going to start by plugging in 0. 3 times anything to the 0, 3, plus 1/2 to the first. Next, 3 times 1/2. Then I'm going to do 1/2 squared next. 1/2 squared is 1/4, and 3 times 1/4 is 3/4. And I'll keep going until when? This time, you don't stop. You keep going. And the only way to indicate that is with this plus dot dot dot. So there's your expansion. Okay, I'm going to mix it up a little bit, and this time ask you to evaluate. And we're going to evaluate k equals 2 to 12. So the sum as k goes from 2 to 12 of 4k minus 3. Make sure you guys can see the sum of 4k minus 3 as k goes from 2 to 12. And I can sit here and plug all of these in, and I'm like, I don't really feel like it. I'm going to plug in 2, 3, 4, 5 and get all these numbers. And that's why I actually changed it to evaluate, because if you can just kind of get it started and figure out where these values are going, then you I want you to know that there's actually a calculator tool to handle this. So we'll say in the calculator. And so in the calculator, you're going to press math. And under math, you can choose a summation. And I'll show you that now. Math, and you can scroll up or way down and click summation. You can see the sigma, and on this this operating system, you actually have everything kind of in position. If you have a different operating system, it might not kind of sit nicely underneath or over, but you still have a spot for everything. So I'm going to put x equals 2 instead of k. And then in the upper bound, I'm putting 12. And then in the parentheses, I need to put the entire explicit rule. So I don't want like the minus 3 out of the parentheses or anything like that. Like I need that whole rule in there. So I'm going to put 4x minus 3. And that's like saying 4k minus 3. And then I can hit enter, and it actually takes all the numbers in the series and adds them up for me to get 275. And if you don't have a calculator, you can write all the numbers out and add them up yourself. So it's not something we cannot do. All right, before we go on, I want to make sure you guys understand how many terms we're expecting to see in some of these expansions. And so I want you to look at number 1 up here. When I wrote this out, I had 1, 2, 3, 4, 5, 6 terms. And this was a sum from 2 to 7. Down here, I'm wondering if you could imagine how many terms this would have been on number 4. So I want us to understand why there were 7 terms here. I'm sorry, 1, 2, 3, 6 terms here. So I'm going to make list this out as 6 terms. And those 6 terms come from taking 7 minus 2. And you're like, that doesn't work. From 2 to 7, that's a distance of 5. How do we get 6? You actually just add 1. And that adding 1 is because we're including that upper and lower bound in the total number of terms. And so that's a note I want you to make down here, that if I ask you to calculate the number of terms, it will always equal your upper bound minus the lower bound, but that number will be off by 1. And so you have to add 1 to account for it including the lower and upper bounds in the calculation. So while we're down here, how many terms are there from 2 to 12? And so hopefully you know to do 12 minus 2 plus 1. There are 11 terms. So if we were to actually expand that one out, it'd be kind of annoying. A lot to write out, but you'd end up writing out 11 terms there. All right, let me turn the page and add a little bit more information to this. I want you guys to be able to write your sigma notation yourself if I give you the sequence. So let me clarify a couple more things with notation. If I give you a sub, let me not put an n, let me put an actual number, a sub 5. This means the 5th term. And it can mean the 5th term in the sequence or the 5th term in the series, because there's still kind of both a list. Series means we're just going to add them up. If I say s sub 5, this actually means the 5th partial sum. And that means the sum of the first 5 terms in the series. And that is basically like saying sigma notation from k equals 1 to 5. And so those two have very different meanings. So I'm going to ask you to find, we are on number 5, to find the 5th partial sum of 2k squared. And writing it that way is another, it's an evaluation question. I want you to evaluate the sum, but you could turn it into sigma notation by putting k equals 1 to 5 on a sigma and 2k squared as your explicit rule. And then when you write out all of these components and add them up, you would have your 5th partial sum. And so I'll go ahead and put some of those down here. We plug in 1, we get 2. Plug in 2 squared times 2. 3 squared times 2, 4 squared times 2, and 5 squared times 2. And then we would add all of those up, and then we would have our 5th partial sum. I can do this without the calculator. Let's see, that's 10. So now we're at 60, 70, 80, 90, 100, and 10 more. So 110. Okay. So now I will switch back over to you guys writing the summation notation. So your instructions might say write in sigma or summation notation. And so for number 6, I'm going to actually give you -2 plus 2 plus 6 plus 10 plus so on all the way to 54. So we have an actual stopping point. And to write this in sigma notation, I'm going to have k start at 1. You can have k start at other things, but it's going to really mix up how we write our explicit rules. So I recommend starting at 1. I don't know when to stop yet. You don't stop at 54. That would be saying the 54th term. That's not what this says. This says some term number is 54. Like the 4th term is 10. The something term is 54. I don't know what that is yet. So I don't have an upper bound. But I can write an explicit rule pretty easily. I think you can tell there is a common difference. 6 minus 2 is the same as 10 minus 6, and so on. And so the common difference is 4. So I can write my explicit rule as 4 times, not n minus 1 now, k minus 1, and then plus a1, which is -2. And then to find this missing piece, I just need to use that explicit rule and set it equal to the output of 54. I want to know, when will I get an output of 54? Okay, I know you guys can do this basic solving, distribute your 4, combine like terms, move everything to one side. You end up getting 4k equals 60, which tells us k equals 15. And so I'm going to stop when I plug in 15. You can double check by actually plugging in 15 to see that you do get 54. Now, none of this actually gave us a sum. I never actually added up those numbers or typed the summation in the calculator. This was just to write that sigma notation and to practice doing that. Okay, another one. Let's say I give you 48 plus 12 plus 3 plus so on, all the way until you get to a sub n. So I'm actually not telling you what that last term is. So I'm going to write sigma notation, k equals 1 to n. I get to put n on top this time because we're saying to stop at the nth term. Next to that sigma notation, I'm just going to put the explicit rule. I'm skipping ahead a little, but I'm hoping you recognize this kind of sequence is geometric. There is a common ratio. 12 divided by 48 is the same as 3 divided by 12. So I know the common ratio is 1/4. That becomes the base to the k minus 1th power. And there is our sigma notation. If you can imagine here, I'll just do an extension from this problem. If that a sub n wasn't there, and what if it was just ... then everything would have looked the same, except I would put infinity on the top. Like that. Okay, so another little side note. I believe we can stop there. I think that covers just about everything for practicing using partial sums and writing things in sigma notation, and also evaluating or expanding from sigma notation. Bring any questions that come up with this or with any of your practice problems to class, and we will answer those questions then. Thank you.